I just thought it worth mentioning that 5 years ago I was also here as a young, impressionable PhD student. And the lineup was pretty similar, but of course I was equally in awe back then. And now I'm here 5 years later as a young, impressionable research fellow. So I'm very privileged to be here, and I'm very excited to share with you the things that I've been thinking about over the last 5 years and hopefully some of the future research directions. So I'm going to spot this. OK. Right. It's fine. Right. So there hasn't been any talks on semiconductors or any sort of real condensed matter today. So I thought I'd take 5 minutes to give, especially the mathematicians in the audience, a feeling for what's going on in these real-world material systems. So typically, perhaps the most pedagogical thing we can do when we start to talk about a collection of ions and electrons that make up a condensed matter system is to write down its Hamiltonian, which, of course, has the kinetic energy for the electrons, the kinetic energy for the ions, the ion-electron interaction, the electron-electron interaction, which is a particularly formidable problem in condensed matter physics, and, of course, the ion-ion interaction, right? And as an undergraduate, when we start to study and understand and get a feeling for what turns out to be a rather large and complicated matrix or Hamiltonian for these strongly coupled systems where you've got electrons, you've got ions, and everything's moving and everything's coupled, we make a few what I would call key approximations. The first key approximation that we make in, I think, perhaps more mathematical language is that there is some operator T of n, which is the translation operator that moves you from some point in real space to a set number of lattice vectors away from where you are right now. And the neat thing about this operator, in the case of crystalline periodic systems, is that it commutes with the Hamiltonian. Right? So the nice thing about that is that we can simultaneously diagonalize T of n and H of n, and we can label the eigenstates of a Hamiltonian by the eigenstates of the translation operator, which are just plane waves. And with this toolkit in our belt, we end up with what is essentially the energy spectrum of this matrix, where you've got a set number of energies as a function of k, which labels the eigenstates. And in semiconductors in particular, you have a pretty large gap between the set of filled eigenstates and the set of empty ones, which we term the band gap. The second key approximation that we make when trying to make progress on, forget solving this problem, but even thinking about it, is the approximation that the electron masses are much smaller than the ion masses. Right? So this allows us to essentially push the energy scales of ionic motion down to 0 and approximate the lattices to be static. So the simplest version of condensed matter crystal physics is that you've got a static lattice and the electrons are frozen, and there's massive translation invariance that leads to Bloch states and essentially delocalized eigenstates for the Hamiltonian. Now, something that I wasn't taught and became apparent to me later in life was that when we make these two approximations, we've really cooked in kind of a length and a time scale into the system that we're talking about. So if we look at our approximation number 1, we can try to think about the length scale we've kind of cooked into the problem as this number n. So I've made it dimensionless on purpose so that no one has to worry about microns, millimeters, and all these like horrible units. And you can just think in terms of 2 dimensionless parameters, right? So n is nice because it tells us, okay, how many sets of lattice sites can I move from where I am and still commute with my Hamiltonian? So another way of saying that is how far away can I go and the system is essentially invariant, right? So n would be on the order of half a nanometer. Yeah, okay, for those who are interested. But it's, of course, system dependent. But what's neat about this is that kind of the n equals infinity limit is what we call the thermodynamic crystal. But you can, of course, have deviations from that. So you can say that, OK, n is just about 1,000. So I move 1,000 lattice sites and things are the same, but after that, something changes. And of course, this grant has been focused on a very interesting kind of disorder, which is on the scale of n equals 10. So you can really barely move before the system is substantially changed. Similarly, on the other side, we can get a feel for the kind of approximation and the time scale we've cooked into the system by considering the energy scales of this Hamiltonian. So the lattice or vibrational energy scales were typically of the order of milli-electron volts. And then there's the gap, which is pertinent mostly to semiconductors, which is on the order of electron volts. And if we take the ratio between these two and call it gamma, you can see that basically, if we set gamma to 0, we've pushed the lattice energy scales down to 0. We're saying the crystal is frozen. If we allow gamma to deviate, this is the dynamic lattice. So now the lattice is moving on its native scales. And of course, there is the limit in which gamma approaches 1. which is what's called non-adiabatic quantum dynamics, where these lattice vibrations can induce transitions across the gap, and that becomes highly complicated, highly coupled system, which I really won't get into today. So if we just look at these two parameters, and I'll try and explain all of the things I've thought about in terms of these today, the question that and I think all of us are interested in is what happens in condensed matter physics when we break away from these approximations. So what happens when n is not infinity, which it in fact is never, and gamma is also not zero, right? So I thought I'd put these up in a nice 2D plot where we've got the perfect crystalline limit on the top, and the short wavelength disorder limit on the bottom. And on the x-axis, I've put the timescales that we're interested in, with, of course, the static lattice on the left and the dynamic lattice on the right. Right? So you can just think about this n gamma as your 2D space of disorder in semiconductors. So of course, bottom left is something that we've spoken about a lot. The landscape is brilliant at this, where you've got these indium fluctuations in what is a gallium nitride lattice on the order of n equals 10. On the top left-hand side, you have pertinent disorder in something called polycrystallinity. So if you try to grow a crystal in a lab, it's quite thermodynamically favorable for a bunch of microcrystallites to form, rather than for your system to be one single translationally invariant crystal. So this is polycrystallinity. And of course, on the bottom right-hand side, we have the limit where we've got lattice vibrations that modify this local translational invariance on a short scale, right? And these arise because we lift the restriction or the limit that gamma is equal to 0. So when trying to explore this kind of landscape of different disorders, the question that arises is kind of what are the experimental toolkits we have, or theoretical toolkits we have to explore this landscape. So on the bottom left-hand side, there's some beautiful work from Claude and co. that show that if you take a local probe very close to a locally disordered semiconductor, you can map out the line widths of the luminescence induced by injecting electrons into these systems. On the top left-hand side, I hope to introduce today a new kind of microscopic tool with which we can try to study the dynamics of electrons on the order of n equals 1,000. And on the bottom left-hand side, I'll introduce some electronic structure calculation techniques that I hope to reveal some insights on dynamic disorder. So disorder that is not cooked into the lattice by imperfections or disorder or doping, but is intrinsic to the fact that the ions are always moving. So with that, these are the kind of projects I'll overview today, and there's no point me getting into them here, so let's dive into the first one. So before we get into the nitty-gritties of the project and the interesting physics that uncovered itself with me as the vessel in my PhD, I thought I'd take a moment to give you a feel for the kind of disorder scales that you encounter when you really deal with semiconductors in daily life. So here's the unit cell for what's called a lead halide perovskite, which is a wonderful material that has amazed semiconductor physicists over the last 20 years because it's extremely disordered, and yet it works extremely, extremely well. So to give you a feel for that, let's take like a micrograph of what's going on. So here's the n equals 10 to the 6 limit. So you can see I put the microns there for anyone who's interested. You can see that even on these scales, right, you can move pretty far and things can change, right, as you can see in this plot. If we zoom in 2 orders of magnitude, again, the system is heterogeneous. Zoom in a little bit more, and you know what? It's still heterogeneous. And as part of this grant, Richard and Yun Liu, a collaborator of mine, and Marcel have investigated what actually happens on even shorter length scales, where you allow this halide site over here to vary as a function of space, which varies the valence band energy. And what they discovered through the landscape was essentially the high kinetic energy of the electrons in these systems pretty much washes out these potential fluctuations, giving us a pretty nice insight into why carriers can move so far and so efficiently in this really disordered class of semiconductor materials. So broadly speaking, there are classes of semiconductors where it's clear that Bloch's theorem doesn't hold on an entire spectrum of length scales, and yet they work incredibly well. Now, one of the interesting things about this material that is a little bit less in the vogue when it comes to the recent literature is the fact that there's lead in there. Apart from, of course, the environmental hazards of using this out in the fields, lead is a fun element to play with because it's got a pretty high atomic number. Now, what this means is that in the frame of reference of the electron that's moving around this heavy ionic center, there is strong what is called spin-orbit coupling. So essentially, in the electron's frame of reference, it sees a strong magnetic field. So that, when you hear a magnetic field, that means that perhaps there are opportunities to do with electronic spin in these materials, right? And that's something that could be very, very interesting. So before we get into what happens in the case of spin-orbit coupling, let's first recap what happens in the case of standard semiconductors. So in most normal semiconducting systems, there are two symmetries that are pretty much hold almost all the time. The first is time reversal symmetry, which takes you from k to minus k and flips your spin upside down. And the other one is having an inversion center, which basically takes you from k to minus k with the same spin. If you put these two together, what you end up with is something called Cramer's degeneracy, which basically is a statement that your band structure is spin degenerate. So essentially, all your eigenstates have a spin up and spin down of the same energy. And this is kind of annoying because this means that you can't really do useful stuff with spin in spin degenerate semiconductors because your eigenstates are spin depolarized. However, in the presence of spin orbit coupling and inversion asymmetry, so you lift the second of these two symmetries in your system, you can write down the Hamiltonian to look something like this and solve it for its eigenvalues and eigenvectors. And what's most interesting is the fact that the spin eigenvectors are no longer degenerate. So if you plot the band structure, or here the eigenvalues for these two what are called spin textures, you find that actually the in-plane spin does something quite interesting. Right? It goes in almost a helix, as you can see on the top right hand over here. So to give you a little bit more of a feel for what this really looks like, I've plotted it in 3D over here. And something that's quite interesting that you can notice is that you've got these two spin texture eigenstates that go one way and the other one goes the other way. But if you look at the direction of the spin, which kind of gives you a sense for the local magnetic field that it's feeling, you realize that this, if you look at the right-hand side, sorry, this is quite hard. Yeah, on the right-hand side of the blue graph, the spin is pointing out, and the left-hand side of the red eigenstate is also pointing out. Right? So that means that essentially the effective spin felt by a given lattice cut of this material is in the same direction, and they're labeled by the orange and green bands over here. And what's neat about this is that when you photoexcite these materials with certain dipole selection rules, so right and left-hand circularly polarized light, so it's basically certain spherical harmonics in the maths language, you end up populating this band structure away from the zone center. So for example, if I choose to optically address this selection rule, I end up with a bunch of electrons sitting on the right-hand side over here. The reason that's interesting is that these electrons on average have a finite momentum, which necessarily gives rise to a finite spin current in one direction. And this is something known as spin momentum locking. Really simply speaking, what this means is that if I photoexcite with right-handed circularly polarized or left, I get spins that kind of flip direction of the current, as you can see over here. And one thing that's important to note for maybe later in this bit is that if you change the spin texture, so you change the direction of inversion symmetry breaking, the red and blue eigenstates will flip. And so the link between the selection rule and the direction of the spin current will change. Right. Now, this kind of very neat band structure physics based on Bloch states and essentially infinite translation symmetry is something that's been really well explored in single crystals. Because in these systems, you can put on metal contacts, you can photoexcite them with these helicities of light that address certain selection rules, and measure these spin currents on the surface of topological insulators, in single crystals, and in these sort of interesting bismuth-silver bilayers. But what about disorder? What's going to happen to these spin textures in the presence of n equal 10 to the 3 disorder? So here is an example of that kind of disorder. You've got these microscopic grains, and in each of these grains, if you zoom in somewhere, you've got a band structure, you've got this nice spin-orbit coupling. But of course, on average, we don't have translational symmetry. Right? So what is the interesting physics that might occur here? So in order to be able to answer this question, in my PhD, I tried to develop a new tool because there are some key challenges. The first is, of course, there's no macroscopic translation invariance, which means I can't slap on contacts at the end of my crystal and say, all is good, everything in the middle is the same. The other problem is that when you photoexcite these systems, the spin relaxation is quite fast. So you need to have an ability to capture these local spin currents on very short timescales. And of course, there's massive micron scale heterogeneity. So I also want to be able to kind of spatially resolve what's going on. So in order to achieve this, we built complicated experiments that I won't go into. But just blurring that out, the broad brush picture is that we developed a ultrafast microscope with which you can photoexcite circularly polarized light into the system. So you basically photoexcite one kind of spin and image both the left and right-hand circularly polarized light through that film post-photoexcitation. And if you subtract those two left and right-hand circularly images, you get a map, where blue is the spin that you did photoexcite and red is the opposite spin. So let me show you some data of what's going on. So just to revise, blue means the spin that I photoexcited, and red is the opposite spin. Before I show you this, it's kind of instructive to think about what would happen what we would expect to happen. We expect that the whole map is going to turn blue, and then it's going to fade to white, right? So here's what really happens. So as we approach the point of photoexcitation, all of a sudden the system looked like this, right? That's a bit weird. Because first of all, why are there red regions? Why are there regions in space where the spin is counterpolarized to the one that I photoexcited? Why is it segregated from the spin that I did photoexcite? So to get more of an intuition for what's really going on, if we look at the time-dependent traces of different points in space, I've labeled blue is the region 1 and red is region 2, you notice a stark difference. In regions of copolarized spin, the signal appears basically within the instrument response function and decays, whereas the counterpolarized regions sort of take some finite amount of time to turn on. And what's neat about this experimental data is you can go and fit this for every single pixel in your system. And for those with a trained eye, you'll see that basically any point in red on the left-hand graph corresponds to a longer rise time on the right-hand graph. Of course, I can plot a histogram to show you this as well. So that was our key strange observation number 1, was that these regions of counterpolarized spin seem to appear after a finite time post-photoexcitation. The other key insights that enabled us to understand what in the world is going on is the fact that when we locally excited these systems, rather than the local electronic population with spin diffusing, it moved in a particular direction. Right? So there was a local in-plane spin current, as you can see here. And most importantly, this can arise from just an energetic landscape with a lower band gap over here that tends to funnel your spins. It has nothing to do with the fancy spin texture band structure. So the smoking gun of that would be that I photoexcite the opposite spin and it moves the other way. And we saw that as well, where here I photoexcited left circularly polarized on the left and right on the right. And you see that all the regions that would arise instantly now take a finite amount of time. Right? So that was our third key observation. And when we put these things together, we were able to explain the data in kind of a very simple toy model, where I just made the assumption that let's say that we have 2 regions in space where we break inversion symmetry, but when you break inversion symmetry, you pick a direction. So you can pick any direction. So let's pick the opposite directions. What happens then is that if I photoexcite a certain helicity of light, I generate copolarized spins in both of these domains. But because the band structures are flipped because of the different inversion symmetry direction, the spin currents will move in opposite directions. And what's nice is that when they scatter, it goes into the opposite spin, which is going to move the other way. So what you get is regions of counterpolarized spin that take a finite amount of time to arrive. And of course, you can just, for the sake of consistency, check for the other spin, and the model works out perfectly, right? So it's quite neat because what it tells me is that all I needed were locally varying spin textures and spin momentum locking in order to get this kind of emergent phenomenon of spin segregation in a pretty disordered material. And with these simple 2 kind of assumptions, I was able to explain all of the experimental phenomenology that I've just gone through today. So broadly speaking, what that explained to me early on in my PhD is that disorder is kind of important even when it happens on long scales. Right? It doesn't need to be local fluctuations. Here, n is 10 to the 3. My translation operator is pretty well defined locally. It's just that when I go far enough, suddenly something changes. So in a polycrystalline grain like this, you can zoom in on the grains and do X-ray diffraction. And you can see that each of these grains are pretty crystalline, but they're kind of oriented in random directions. And what that leads to is a landscape of symmetry breaking that happens in random directions. And that leads to this kind of emergent phenomenon of local spin segregation, the formation of spin domains on really fast timescales. So that was quite fun, I thought, because obviously influenced by the ideas behind this grant, I was very interested in what happens at the intersection of disorder and cool electronic physics. And immediately, something showed up. Moving on to kind of the other side of my PhD, where I tried to look at things from more of a computational and theoretical point of view. Here we've kind of established that if you break the n equals infinity limit and just set n equal to 1,000, something cool will happen. So now on the other side, we're going to try to ask the question of what happens when we allow the lattice to actually move in a standard semiconductor with absolutely no defects. So this is a perfectly crystalline system, infinite translation invariance. But now I'm allowing the ions to move a little bit on their natural energy scale. So before I dive into that, maybe it's a little bit instructive to look at the idealized case of a really important application of semiconductors, especially in today's climate, which is photovoltaics. So the way photovoltaics work in the simplest, most cartoony picture of all time is you shine light on a semiconductor, those excites electron and hole pairs, which then you collect at a finite voltage. And because current times voltage is power, you've extracted power from the sun. Now, if we do this from a standard old school semiconductor physics point of view, what you can realize is that post-photo excitation, you get these electron and hole pairs that are sometimes above the band gap, but they rapidly cool to the band edge through emission of phonons and scattering with other electrons. But what that means to me as a physicist is that the electrons and holes are sitting at a finite chemical potential, which I should be able to extract. So in other words, the voltage that I should be able to extract from a system like this should be the band gap by the electronic charge. In real system, it's never this. It's never zero. The difference between the voltage that you extract and the band gap over Q is never zero, even entropic considerations aside, which is a side note. But basically, this is not zero. So the question was, why is this, right? And the first kind of hint as to what's kind of strange about these systems that we maybe didn't take into account is we start to look at the first process in how a photovoltaic works, which is light absorption. So I've plotted on the right-hand side over here the latest and greatest in photovoltaic semiconductor technology and all of their absorption spectrum. So barring silicon, which has a completely different absorption process, you can see that all of them have pretty sharp absorption onsets. This is a log plot, right? Especially gallium arsenide. It's like incredibly sharp. But an important thing to note is it's not infinitely sharp. The absorption is never identically zero below the band gap, right? So something is going on in these systems, and the measure of this energy scale over which the absorption decays to 1 over E of its value is something known as the Urbach energy. And this Urbach energy turns out to be empirically an excellent indicator of how much voltage you will lose from your band gap when you build a photovoltaic cell. So it's a bit of a hectic graph, but basically on the left-hand graph, I have, on the y-axis, I have the voltage loss from the band gap, and on the x-axis, I have the Urbach energy. And you can see there's a pretty solid scaling between these two, right? So the longer this Urbach tail of yours, the more voltage you tend to lose in semiconductors. Now, in the case of locally disordered n equals to 10 disorder semiconductors, we know this is true, as has been investigated by this grant in amazing detail. So this is 2 different indium concentrations, and if you measure the log absorption as a function of energy, you see that as you start to put in more and more indium, you change the scale over which the crystal is non-periodic. And of course, the Urbach energy changes. It can be seen even more clearly over here, where you can see that the more indium content you put in, the Urbach energy goes up. So I'd say, broadly speaking, in the case of pure static disorder, where I've let the crystalline lattice be perfectly fixed and unmoving, Urbach tails are pretty well described by n equals to 10 compositional fluctuations in real space. This is something that the landscape is incredibly good at being able to pick up, right? However, if we look kind of back in the literature to even the name Urbach tail, we can look at Franz Urbach's first paper, where he mentioned, where the Urbach tail comes from in basically 1953 at the Kodak company, where he was studying these silver bromide films. And even there in figure 2, he makes a very interesting observation, which is that as he changes the temperature of the system, the Urbach tail changes quite substantially. Fast forward to the generation of 3 5s, and this is just pure gallium nitride. There's no indium in here, right? This is a perfectly crystalline system. Again, I change the temperature of my system, and the energy scale over which my absorption drops below the band gap changes substantially. Fast forward to the era of color images in journals and these latest halide perovskites, the same physics holds true, right? And so basically over the last almost 70 years, we've had this empirical insight that temperature fluctuations have something to do with the subband gap absorption tail. So part of my PhD was trying to understand whether we can capture Urbach edges due to lattice vibrational disorder. So in other words, you take perfectly sharp eigenstates and you average them or trace over the lattice vibrations in the system. And the question that I had was, will we get Urbach tails, right? So just to give you a notion of how we actually do this, I thought I'll go into the toolkit, because this is not a trivial problem that the toolkit already exists for. So broadly speaking, when trying to study finite temperature effects on electronic structure in condensed matter systems, we bring back the old Hamiltonian, and we break it into 2 bits. So what we do when we make this approximation, when we separate the nuclear and the electronic parts, is basically the same assumption as before, where we say the electrons are much lighter than the nuclei. So at every nuclear configuration, the electronic Hamiltonian diagonalizes that particular configuration. So because it moves so slowly, you can use adiabaticity to say that these electronic eigenstates adiabatically follow as the ions are moving around. So the left-hand side, which is basically the electronic Hamiltonian for a fixed nuclear configuration, can be solved by using something called the variational principle, which basically means for any trial wave function, the ground state is the lower bound of the expectation value of the energy, And what's fun about this is you can put in as many parameters as your computer will allow and just basically do gradient descent in n dimensions, and you should hopefully get your ground states. Obviously much more complicated than that. And for the nuclear Hamiltonian, what we do is we basically take a harmonic expansion of this, because this is, again, 3n dimensional energy landscape, which is computationally challenging, and that leads us to nuclear eigenstates, which in the case of a harmonic expansion are the states of a harmonic oscillator, right? So Hermite polynomials. And with these two kind of bits of toolkits, we can put them together, because the right-hand side gives us a configuration, a probability density for the different nuclear configurations in our system. And for each of them, we can solve the electronic eigenstates and basically trace over the different nuclear configurations. So it's quite a powerful toolkit, because it means that any experimental crystal structure that you give me, I can compute finite temperature observables, of which the finite temperature Urbach tail is one. It's just important to note that these are also expensive calculations. So the scaling goes as approximately number of electrons cubed. I mean, you can make it better with some Fourier transform magic, but it's still polynomial time. It's not going to be great. So broadly speaking, just to give you a visual idea, we've got this system that's fluctuating on some time scale. We don't know what its band structure looks like, so we freeze it. We calculate its bands. We pick another configuration, do the same thing, and do this over and over again until we've converged a finite temperature band structure for the system. And the question that I had was, if we do this for a perfect direct bandgap semiconductor, will we get Urbach tails, right? And the nice thing about density functional theory or electronic structure methods is that we have full access to the wave functions of the system. So once I capture the Urbach tail, I can go back and ask, okay, were the tail states in this Urbach tail, are they exponentially localized? Are they Anderson localized? Seems counterintuitive, because of course the disorder strength is not high enough, and it's not static, which is the Anderson case. So we can actually investigate these questions. And another important question from a materials point of view is which phonons contribute to this Urbach tail? Because of course, if I can reduce my Urbach energy, I can make myself a better solar cell, right? So with that in mind, we kind of threw a huge amount of computational power and some clever tricks with regards to how we sample a Brillouin zone. And we were able to successfully capture an Urbach tail in a direct bandgap semiconductor. So this is a full inorganic perovskite material, where you can see that, first of all, there's a huge number of absorption events, and these exponentially rare Urbach states, they take a long time to show up, right? But you do get an Urbach tail at the end of the day. And what's neat about this is another insight we had was that if you look in K-space, electronic eigenstates away from the band edge also contribute to our Urbach tail. So what this means is there's a pocket of electronic states in our band structure that contribute to this finite temperature Urbach tail. This is true across material systems. So to make contact with the ground, we did some stuff on pure gallium nitride, and again you get an Urbach tail. Again, you can see that states away from the zone, the band gap also contribute quite substantially to the Urbach tail. So when trying to sample different nuclear configurations in a given system, an important consideration to make is the fact that the nuclear distortion can have a length scale that's larger than a unit cell, right? For example, acoustic phonons. If you move every single unit cell the same way, you've just moved your whole system. So of course, you need to have a finite wavelength to these phonons. So that's another question that we were able to answer, where this is the Urbach tail you get for the unit cell of gallium nitride. If you double it to capture longer wavelength fluctuations, the Urbach tail changes substantially. That was a surprise. Keep increasing the size of the unit cell until your computational time runs out, and you find that you can kind of converge an Urbach energy. But this big surprise was that these finite momentum phonons, or kind of finite wavelength distortions of the crystal lattice, do substantially renormalize your Urbach tail. This is true across materials. So we did this again in the halide perovskites, where again you can see there's a substantial renormalization in the Urbach tail as you start to include larger wavelength distortions, right? And the way that we understand this is really kind of quite simple in a sense, which is that we've already established that there's basically a collection of electronic eigenstates around the band edge that contribute to our finite temperature Urbach tail. So if you think about two electrons within this pocket in your Brillouin zone, they're going to be separated by small momentum wave vectors, right? K1 and K2 are close, so K1 minus K2 is going to be small, which necessarily means that the phonons that scatter between these two are going to have a small q vector, and q is 2 pi over lambda, so a large wavelength. So that was something that was quite kind of surprising to us, is that first of all, states away from the band edge contribute to the Urbach tail, and the second is that these finite wavelength distortions substantially change the value of your finite temperature Urbach tail. With all of this kind of done, we were able to answer kind of new interesting questions about these systems. For example, which phonons contribute to the Urbach tail? So what I'm showing you over here is, again, a bit of a busy plot. But the simplest way to think about it is that on the x-axis, I have different, let's say, nuclear configurations that I have sampled. And you can see that in the main absorption, all of the configurations pretty much contribute equally to my absorption, which makes sense. No single nuclear distortion is going to substantially change my bulk absorption. If you look in the Urbach region, however, the story is quite different. There are certain configurations that did us a great help in converging our Urbach tails. For example, configuration 37, right, really pulled states into the Urbach tail. And because each of these configurations is essentially a superposition of my 3n phonon modes, what I can do is I can invert this relationship to ask which particular phonons were present in these modes that pulled me into the Urbach tail. And the answer is, again, surprising. It's not all the phonons. They don't all contribute equally. There are certain phonons, as you can see, the 4 ones I've circled out over here, that have particular mode energies that really tended to pull me into the Urbach tail a lot more than the average, almost 2 to 3 times more. Now, kind of putting these ideas together, what that means is that it's clearly a multiple phonon effect. By just displacing along single phonon trajectories individually, you cannot capture an Urbach tail. So clearly, it's a multi-phonon effect. And clearly, you require finite phonon wavelengths. So if you think about a collection of objects with finite wavelength and the fact that you need more than one of them, you can think about the Fourier transform of that, right? Now, what that really means is that in real space, there's likely a local compression or dilatation to the crystal lattice that's lowering my band structure enough that I'm pulling the band edge into this Urbach tail that's purely from dynamic disorder. Right. So that was kind of the conclusion of that bit of our story where we realized that dynamic disorder plays a huge role in all of our Urbach states. Now, with my remaining time, I thought I'll give you a flavor for what I'm planning to do next and how it connects also to, in some ways, ideas that I've pulled away from this grant and this amazing collaboration, which is that everything on the right-hand side of this plot in my PhD, I was only able to do with theoretical techniques. I didn't really have experimental tools to do anything on that side, right? So the big question I had towards the end of my PhD, my big frustration was, can we access these statistical, stochastic fluctuations of the crystal lattice experimentally? So can I see how does my Urbach tail dynamically form in real time in real experiments? So before we get there, kind of another important thing to note is that yes, Urbach tails arise from dynamic fluctuations of the crystal lattice, but equilibrium fluctuations are just generally very important in physics. The reason for that is a famous relationship called the fluctuation dissipation theorem, which basically tells me that the susceptibility of my system, or its imaginary part, which links back to kind of Terence Tao's first bit of the talk, is what drives dissipation in my system, right? And what's written on the right-hand side of this is basically the correlation of some local variable integrated over time. So essentially, if I can understand the correlations within fluctuations of my system on their native timescales, I can understand exactly how energy is being dissipated. So just to give you a flavor for why this relationship is even true, a nice intuitive example is Brownian motion. So here we've got a bunch of pollen in water, and molecules are bumping into it all the time. So its local central position is moving around, but it's on average in the same place, right? And the fluctuation dissipation theorem makes a pretty profound leap to say that if I were to tie one of these Brownian particles to a little string and drag it through the water, it's going to have some viscosity, and that friction due to the viscosity is going to dissipate some heat. But I've added no new microscopic physics to my system, right? I'm just pulling this pollen particle through the water. So what it's saying is that this friction-induced drag or viscosity is directly the same physics. It's the same microscopic fluctuations of molecules bumping into my pollen particle as it happens at equilibrium. The same is true for electrons in materials, where the electrons fluctuate for a black body, and recombination is what dissipates. Same is true in electrical engineering, where if you connect a resistor up to an oscilloscope, you'll see that there are voltage fluctuations, and it's the resistance that dissipates the heat. So really, fluctuations are a pretty rich area of physics that would be nice to be able to experimentally capture, because they're the reason things aren't efficient. They're the reason that energy is dissipated at equilibrium in systems in general. So the big question, therefore, is kind of how do we measure things in time? Do we have a toolkit with which we can access these dynamic fluctuations? So just to give you a sense of scale, we're really looking at fluctuations on, I'd say, these time scales, right? So a lot shorter than astronomical time scales, and far from any experiential time scale of like milliseconds. So just to give you a flavor for how we've done this in the past, The first person ever to do this was a famous photographer known as Edward Muybridge, who was challenged by Leland Stanford from Stanford University, the founder, to try and image a horse running at full speed, because Stanford wanted to make his horses as fast as possible, right? So there was a big prize for this. And with this was the first kind of ever motion picture on a non-experiential timescale. If you were to look at a horse running, you wouldn't see that. This is a slowed down version. You can see that, in fact, all 4 legs are in the air. So that was good. And we've pushed this kind of technique of measuring things on really short timescales to the picosecond regime, and even to what's now the attosecond regime with the recent Nobel Prize awarded for this, right? Where we can now measure the electric field of a light pulse on a billionth of a second, so extremely short timescales. And just to give you a flavor for the relevant timescales that we're interested in, it would be somewhere in between these two, because these are the timescales on which a carbon-carbon double bond does a full round trip. So broadly speaking, the way that we've pushed these techniques to these incredibly short timescales is through something known as the pump probe style approach, because no camera in the world can do a billion frames a second. No electronics is good enough. So what you do instead is you say, okay, my camera is slow, but I'll have a flash that's really fast. So what you do is you perturb your system with the pump, which is what's in blue. So you start something off, and you take a snapshot at one time, and that gives you your first data point. You do it again, but now at a different time you take a snapshot, and that gives you a next point, and so on and so forth until you've built up a nice picture of what's going on in your system. This is similar to kind of, I think, the experiments that Alan has shown in the morning, where they release the gas, they measure its size, they do it over and over again. Right? So this is the approach, broadly speaking, to measuring ultra-fast things in physics. And with this kind of approach, you can measure really unbelievable phenomena. So for example, what you see over here are the time-dependent traces of an organic molecule that's been photoexcited. And what you see, all these oscillations that look like noise, aren't actually noise. Those are the normal modes of the system that are vibrating in real time. So you can build sort of ultra-fast femtosecond molecular movies of what happens upon photoexcitation in a system. And just to give you a flavor for what I've done in the last years in my research fellowship, is we've pushed this technique to new length and time scales, where we've asked the question of not what happens after you photoexcite, we've asked the question of what happens during photoexcitation. Can we pick up attosecond physics of how actually these Rabi cycles happen within materials when you've got an oscillating electric field going through them? So what I'm showing you over here is an absorption image of a 2D material. And what I'm going to show you is how we built a microscope which is capable of measuring the electric field down to 100 attoseconds of light propagating through this 2D flake. Right? So this is basically the electric field is going to oscillate as we move through time. And we see something quite neat, which is that only as we approach the peak of the field does really the flake appear in all its greatness as it does in the standard absorption image. So you'll see now that the flake really appears and then it disappears. And what's cool about this is basically we're looking at driving a system and looking at the response of the polarization back on the system. So we can ask interesting questions about causality and other such things within this setup. For example, if I photoexcite over here, I know the real and imaginary part of my refractive index are causality related to each other. But how far away is that true? Because, of course, my electronic eigenstates are extended. Right? So will causality post-photoexcitation over here be seen over here? What is the time scale? Is there a light cone? Does the electron screening slow that down? So these are the questions that we're looking at in our lab today. But so broadly speaking, this is the power of the pump probe style approach. Right? You can really see things on ultra-fast timescales, but only post-photoexcitation. So the question that I had towards the end of my PhD is I've generated all these femtosecond and now attosecond movies, and I keep calling them movies, but it's a little bit of a conceit. Because are these really movies? Right? That was the question that I was asking. And in order to kind of answer that, let's make connection back to our horses, right? And look at how did Edward Muybridge actually make this video. The way that he did it was he set up a bunch of cameras on a track with metal wires across, and as the horse ran past, it triggered each camera to take a shot one after the other. So it was a correlated set of sequential snapshots of the horse running in time. What if we tried to do this with our pump probe style approach? What would we do? We'd launch the horse, take a photo 1 millisecond later. We'd bring the horse back, we'd launch it again, take another photo at 2 milliseconds. And we'd end up stitching these together into what's kind of an incoherent mess of how a horse actually runs. So this will tell me, yes, horse moved from point A to point B, but all the local correlations between the legs and how they actually move is fully lost. And of course, if you average this out, then you're left with really pretty much nothing, right? So the big question that I had for the next bit of my scientific career was, how do you really measure ultrafast, what I call film reels? So true femtosecond or attosecond data, but in lab time, so on my watch, not in some stroboscopic time with related to something else. So broadly speaking, as I've discussed, we kind of need three key or like essential attributes to our new toolkit that we're trying to develop. The first that gives us an ultrafast data stream. The second that is non-perturbative, because no one wants a perturbative probe. And the third one is that, of course, we want to look at equilibrium fluctuations, so the material needs to remain at equilibrium. So as discussed, pump probe is great because it's non-perturbative, because you can repeat this experiment billions of times at each time point, right? And your signal to noise is Personian, and you can really push your 1 over square root n down to as low as possible. The bad news is it's not an ultrafast data stream, as I've just shown you. And the worst news is that you cannot do this at equilibrium, because everything is with reference to pump. If you remove the pump, there's no meaning to time in your lab anymore, because you've pinned time zero, you've pinned the phase of everything you launched off to your pump. Luckily, there's a second field that didn't really take off, but it's something called single shot spectroscopy, where you generate a bunch of pulses that are truly one after each other in lab time on these femtosecond or attosecond timescales. And that's great because it gives us an ultra-fast data stream. The bad news is that you have to do your whole experiment in one laser shot, which means you need extremely high photon fluxes, and the probe is basically not perturbative. So this is kind of a technique that's been broadly used to study things like fractures and explosives and things that are clearly out of equilibrium, right? So with that in mind, kind of, is this the end? Is there no way past this? And so let's do like a little thought experiment or a little simulation that I set up, where here's my crystal system that's vibrating with 4 normal modes, right? And I do one single shot noisy experiment, as I'm showing you over here. So the traces in black, as you can see, they're perfectly periodic. They are the 4 normal modes of the system, where I've picked a random number for the amplitude of my mode and a random number for the phase. Because each time I repeat this experiment, there's going to be a random phase difference between these modes. However, we do know that for a phonon to be well defined, it does need to oscillate over at least a few periods, right? That's going to set its line width. So we know that on short enough timescales, these lattice vibrations are indeed coherent with each other. So we know that each of these snippets, as I call them, will have oscillations in them, but snippet to snippet, the phase is going to be random. So of course, you average these guys together and take a Fourier transform to try and get some mode information, you're going to get nothing, because you've averaged a bunch of random oscillating sine waves, and they're going to average to 0. However, an interesting and perhaps quite trivial math fact that I thought about is the fact that there is a class of functions such that the function of the average is not the average of the function. It's pretty much any nonlinear function, right? So a Fourier transform, if I do the Fourier transform on each of these and I average it, I'm still finished because the Fourier transform is a linear function. If, however, I do the Fourier transform power on each of them, which is CC star, so it's obviously nonlinear function, all of a sudden my modes emerge. So the idea is that if we can extract single shot snippets of this stochastic behavior in our system, perform some sort of interesting nonlinear function on them, so that can even be the 2-point correlation function or the n-point correlation function, if you're interested in that, and average that, then we can still get out really important, interesting information about the ultra-fast equilibrium fluctuations in our system. So the way that I actually plan to do this, which is for only maybe a few people who are interested in experimental details, is that we can take a single pulse from our laser, compress it down to a few optical cycles, shine it on a stair step. What's neat about this is that, of course, the speed of light is finite. So it takes a little bit longer to hit each of these stairs. So what you do end up with is a beam with position-encoded delays. You put that through a lens that's a Fourier transform engine, and what you end up with is a nice fact that in the focus, all of these pulses will pass through, one after the other. You can map that back onto a linear array, and what do you have? From a single shot of my laser, I have a single snippet of ultra-fast fluctuation information. And if I perform the nonlinear function on this and average that together, I can hopefully find out things about 2-point correlators, n-point correlators, and other interesting stochastic information about how the true nature of fluctuations in my material. So an analogy for this is that people may have used an oscilloscope at some point in their life. And you see that there's noise on your oscilloscope and you call it noise. And you can zoom in on the x-axis and you can move down to maybe, if you have the best oscilloscope, picoseconds, 100 picoseconds, right? Because electronics is not fast enough. But really the idea here is that if you zoomed in to the true native timescales of vibrations in your system, that is the source of the noise. So all of a sudden, there should be correlations within the noise. It's not going to be truly white, right? So in the spirit of the speckle, in some sense, this noise is not perfectly uncorrelated down to 0 timescale. So if we can pick up those correlations, we can try to understand new physics. For example, in these halide perovskites, we could try to understand on what lengths and timescales are these phonon fluctuations that give rise to this dynamic Urbach tail. And there's a whole myriad of other interesting physics across both semiconductors, superconductors, and quantum information where, of course, quantum coherence is lost to a bath that is fluctuating. So broadly speaking, the cool questions that we can ask in the scheme of dynamic disorder in this field is, how did the Urbach tail form? How long did it take to form? Right? Can we actually watch in real time the fluctuations that pulled my band gap well below what it should be? Can we try to understand at equilibrium? We know we have many phonons, many vibrations in a system. We don't really know how coherent they are with each other at equilibrium. Of course, there's a finite coherence. It can't be 0. But how coherent are they? And another really important question in semiconductor physics is trying to understand, once you photoexcite something, how it thermalizes with the lattice and cools to the band edge. Because this is one of the key assumptions that leads to the ultimate efficiency limits of photovoltaics today. So with all that in mind, I'll just add on one last super exciting and kind of side note, which is that in this entire scheme of measuring ultrafast physics, I don't have a pump. And that's a big win as a laser scientist, because I don't have a photoexcitation that I need to start off a process in order to be able to watch it happen really fast. So ultrafast physics has been really, really successful at studying processes that can be photoinduced. So we've studied photosynthesis. We've studied photoisomerization. But there's a whole myriad of other ultrafast processes in chemical reactions and in biology that happen on really short timescales that we're entirely blind to because we can't trigger them with an optical pulse. But with this technique, hopefully we can try to understand the correlations and fluctuations of the endpoint correlators on very short timescales to figure out what's going on in these systems. So is there a metastable state in a chemical reaction that's formed for 100 femtoseconds that suddenly disappears? That is something that might be visible with this technique. And with that, I'd like to thank all my great collaborators, of which Bing-Can Lee, I must point out, is the one who did a lot of the calculations in the dynamic Urbach part recently. And just note that I'm starting, as Marcel said, a group leader position at Harvard in December. And if anyone is interested in any of the stuff I said, I'd be super happy and excited to host for as long as you'd like. And with that, I leave you with the 2D plot of all the kinds of disorder that interested me, where we've captured this polycrystallinity, spin domain formation, Urbach tails from phonons, and this maybe ultra-fast equilibrium thermodynamic approach to studying material systems. And I thought I'd put up also all sorts of other things that I never had the time to explore, but I think are super interesting. Thank you.